Today's webinar, the importance of indoor air quality. So we'll start with a general overview of indoor air quality. So we'll look at its impact on health and well-being, the different types of pollutants that are typically measured, the impact our building choices can have on indoor air quality, and also some relevant certifications and standards concerning indoor air quality as well. We'll then move on to a live demonstration of indoor air quality assessment using an IESVE model. So we'll set up and run a simulation using the Indalo navigator within the IESVE and look at the different options we have to view and analyze our results. So just a bit of context about air quality in general. It's a worldwide health issue, accounting for around 9 million deaths each year globally. So statistically, half of them are caused by outdoor air quality, and the other half would therefore be caused by indoor air quality. So you can breathe air indoors that is up to 8 times more polluted than air outdoors. So the reason for this is because you have volatile organic compounds, VOCs, indoors, which are mostly emitted by furnitures and materials in the building, so are naturally more concentrated indoors. Polluted outdoor air can also be brought into our indoor space by ventilation, etc. So 92% of the people in the world breathe unsafe air. So this is a global issue that's not just dependent on particular countries. As you can see in the graphic there, almost every country in the world is affected to varying degrees. So there's several kinds of pollutants that we consider when it comes to indoor air quality. There's physical ones, chemical ones, biological, so virus, mold, etc. So we'll look at some examples of these pollutants just to be clear on what exactly we're talking about and why they're so important to consider if you are a building designer. So first of all, there's carbon dioxide, CO2, which of course is a very well-known pollutant. So when we are breathing, we're emitting CO2, humidity, and a few other VOCs. So the amount emitted depends on the occupant's activity levels. So this is of interest because there is a decrease of cognitive capability and employees' productivity depending on CO2 levels. There are recommended thresholds for CO2. So each country slash region has its own value. In general, this threshold indoors is below 1000 ppm. And CO2 was used as a proxy for COVID risk during the pandemic, as it indicates indoor confinement and is a rough index of air renewal. So a sufficient air renewal rate equates to a decrease of viral charge, concentration, and therefore a decrease of COVID transmission. So when we refer to VOCs, we're talking about a large family of carbon-based compounds which are emitted into the atmosphere. There is a continuous emission of VOCs by materials and furnitures to the indoor air, such as benzene, toluene, and formaldehyde. There can also be one-off emissions by occupant activity, like cleaning, cooking, etc. So risk can be different depending on the VOC in question. Formaldehyde, for example, is a known carcinogen. Benzene is regulated to be forbidden in construction materials and actually any kind of product in the world. We used to measure total VOC as a family of VOCs, as it's hard to measure each one separately in real time. So the recommended threshold on the slide there is referring to total VOCs. And each label certification scheme has its own values. For example, in France, you can view a VOC rating label when choosing your materials. You can see that on the screen there. So building leaks and ventilation bring outdoor pollutants indoors. Sometimes outdoor pollutants can be filtrated by ventilation systems, but not all of the time. The mainly regulated pollutants are particulate matter, PM, which is mostly emitted by combustion processes. So heating, traffic, agriculture can also be sort of desert sand, sea salt, etc. Nitrogen dioxide is also emitted by combustion processes. Ozone is formed by the reactivity of nitrogen dioxide and UV light and outdoor VOCs. So it's not a directly emitted pollutant, but it is regulated as it has impact on health and oxidation of materials, etc. So you can see the recommended thresholds by the World Health Organization for all of these VOCs on this slide there. So mold is really important because it's a health issue. Mold produces mycotoxins impacting health. The risks associated include eye, nose, and throat irritation, sinus congestion, wheezing, coughing, increased frequency and severity of asthma attacks, chronic fatigue, headaches. So mold formation depends on humidity, surface temperature. Therefore, its formation rate increases with poorly ventilated rooms, also at thermal bridges. It will impact the structure of a building and the materials themselves. For example, the materials' thermal properties can be impacted. So as a building designer, your choices impact indoor air quality. So you're probably accustomed to making choices for thermal performance and energy efficiency, not so much for indoor air quality. So air tightness and ventilation impact air quality. Air tightness affects how indoor and outdoor air are exchanged. Ventilation strategy will also affect this. So there are a lot of factors when it comes to our ventilation strategy that will affect indoor air quality, such as airflows, filtration, and the quality of that filtration. Um, the global strategy in the building. So are we extracting the indoor air? Are we supplying fresh air? Are we using a dual flow system? Are all the rooms efficiently mixed or renewed? So the recirculation rate can be changed depending on the type of project. For example, in commercial projects, we often want to recirculate the air, which reduces fresh air because this is energy efficient, but this can have an effect on the indoor air quality. The ventilation program also has to be considered. So are we ventilating all the time? Are we scheduling, or are we using demand controlled ventilation with, for example, a CO2 sensor or a humidity sensor? And something we have far less choice and control over as a building designer is the environment. So what is the outdoor air quality like? This will obviously affect indoor air quality. So weather factors such as wind speed, temperature, humidity, wind direction will also affect the exchange between indoors and outdoors. So if we want to achieve good indoor air quality, we have to take care of all of these factors. The best way to do this is to simulate it during early stage design and not let it be an afterthought when the building is already constructed. So for certification schemes, labels, etc., there are a lot of requirements. BREEAM, for example, is an indoor related practice, so you get points for the ability for natural ventilation, the choice of low VOC emission materials, innovation, or beyond best practice. There is also a requirement for results. So this involves measuring the concentration of total VOCs and formaldehyde before the building is occupied. Then LEED certification also has results requirements. These are similar to BREEAM, but for more pollutants as listed on the slide. And we can see that VOCs are assessed not as a family, but each individual VOC is listed and measured. And then there is a French certification scheme called HQE, which has similar requirements to BREEAM and LEED. However, the advantage of this certification is if we perform an indoor air quality simulation and measure our results for the required pollutants, then we get the points directly. We don't have to measure indoor air quality when the building is finished, unlike with BREEAM and LEED, making the simulation even more valuable to us. And then in the UK, the British Standard 40102 sets performance requirements for indoor environmental quality, with indoor air quality naturally being a key component of this. So it provides guidelines for maintaining healthy air by specifying acceptable levels of pollutants like CO2, VOCs, particulate matter, as well as ensuring proper ventilation and humidity control. So to achieve this, the standard places emphasis on continuous monitoring, use of low emission materials, and regular HVAC maintenance, with the ultimate goal being to support occupant health, productivity, and well-being. So now just some background information about the different software that we'll use today, starting with Indalo. So Octopus Labs developed the Indalo simulation software in 2012. The main framework is named Inca Indoor, which started off as a research project. It deals with 750 plus VOCs separately, as well as particulate matter. It also deals with ozone, nitrogen dioxide, and many other inorganic compounds. All of these pollutants can react together with each other. So Indalo takes into account more than 2,000 chemical reactions. They account for the transfer of pollutants room from room to room, from outdoors to indoors, etc. So they care about the interaction between pollutants and surface. They also account for the interaction between light and pollutants. This can cause a reaction which will affect the oxidizing potential of indoor air and oxidize some VOCs to have more impact on health. So this calculation engine is wrote as a plugin of the VE with open data incorporated. So we have data about outdoor air quality worldwide, data about material VOC emission. This is data provided from the partnership between materials producers, manufacturers, and Indalo from certified measurements. The software has been validated multiple times since its inception. There have been several field campaigns measuring 60 VOCs separately, so from ozone, particulate matter, nitrogen dioxide across varying building typologies such as commercial buildings, schools, houses, flats, etc. So the system has been very well validated. And we'll also be using the virtual environment, also known as the IESVE, or just simply the VE. So for those of you who are not already familiar with the virtual environment, it is a suite of applications used for the design and retrofit of buildings. The majority of these applications are based around a central geometry model, which we can either create natively using the model application, which we'll have a look at during the software demo, or we can import it from an external modeling software. So typically this is going to be Revit, SketchUp, can even be Rhino as well. So using this model, we can undertake analysis such as sunlight daylight studies, dynamic thermal simulations, compliance checks, and much more. So to save you having to produce another model for indoor air quality, Octopus Labs partnered with ourselves at IES to integrate this analysis using your VE model. So whether that model was originally for compliance, overheating, daylighting, it doesn't matter. It can still be used for indoor air quality analysis. So we'll now just move on to the software demo to have a look at how this integration actually works. So here I've loaded up an existing VE project, which is a model of a school building. So first of all, I'll show you an example of modeling ventilation within the VE. So the building we are considering is mechanically ventilated, and we're going to investigate the levels of CO2 within a typical classroom depending on our ventilation strategy. So UK guidance for school building ventilation strategy would be a CO2 sensor, which is great for reducing fan use, therefore reducing the energy consumption associated with the fan. However, this reduces air exchange in the room. So we will consider a couple of options for ventilation controls. So that'll be a CO2 sensor and a timer clock. We will then be able to investigate the associated levels of CO2 for each of these strategies. So for those of you who are not familiar with the VE, we start by creating our model geometry. So we can either create this natively within the software using the modeler application, which is what I've got selected here, or as I was saying, we can import it from an external modeling software. So yeah, typically that's Revit, SketchUp, or Rhino that we see users bringing their models into the VE. And once we have our desired geometry, we then have to assign data to it. So although our VE model is just a wireframe model, as you can see, each of these surfaces has a construction assigned to it. So in our construction database, I'll just select select our external wall here, and we can see this is made up of material layers, allowing us to accurately assess heat losses and thermal inertia. We can also create and assign thermal templates to define the thermal behavior of our rooms as well. So how they are controlled, heating and cooling set points, internal gains, flow rates for natural and mechanical ventilation. You can see across the tabs there. Alternatively, when we're talking about natural ventilation, we could alternatively use the macroflow application here to apply opening profiles to our models, our model openings to more accurately simulate natural ventilation. But for today's demo, we're not going to be using macroflow. So yeah, for this demo project here, I've created a classroom thermal template, including internal gains such as people, as we can see here, and lighting. which follow a typical school day operational profile. So for example, our spaces will be occupied with students from 8:30 to 4:30 with a lunch break in the middle of the day, Monday to Friday. So I've created two classroom thermal templates actually that are identical to each other than the ventilation control option. So one template is controlled by a CO2 sensor and the other a time clock. So the CO2 sensor ventilation variation profile here, it uses a formula profile to set a CO2 threshold that will activate our ventilation once that's met, whereas the timer clock profile here is a modular profile that is set to, so I'll just actually show you this variation profile here. So it's set to 100% between 8 a.m. and 6 p.m. and it's 40% out with those hours for our ventilation. So after we have set up our model, we can run an annual dynamic simulation using Apache Sim. So I've actually done this in advance just to save us some time today. So I've ran two different simulations for each of our ventilation strategies. So if we switch to Vista Pro, which is our results viewing application, we can see these two simulation results files that I've ran previously. So I'll just select both of these and then we can choose which results categories and variables that we want to analyze from our results. So if I'll just select, yeah, I've just got a sample classroom selected here, just like this one, and then we can view, for example, the respective CO2 levels within the virtual environment. So I'll just select that variable and we'll just view our CO2 levels on the 6th of January, for example. And we can see that so we can see that we're having a very similar amount of CO2 using both the CO2 sensor strategy or the time clock strategy. There's not much difference between them in terms of the CO2 levels in our sample classroom there. And we can also view the ventilation flow rate within our chosen classroom as well. So I'll just select auxiliary vent here. And again, I'll just use the same chart. However, with this, we can see a very different amount of ventilation depending on the control strategy. So the CO2 sensor is achieving an overall lower flow rate throughout the day, as we can see, it's turning on and off with the CO2 levels. So this is what we would want if we were designing to reduce the energy consumption of the fans. However, this may not be the most suitable option for diluting other pollutants. So to consider the indoor air quality in more detail, we can use the same VE model that we're looking at here to undertake a far more comprehensive indoor air quality analysis using Indalo. So to do this, we'll select the Indalo navigator here from our drop-down menu. And this takes us through this entire process step by step. So at the start here, we can see there's a link to a full guidance document which we can use as well for the import to Indalo. And after entering our Indalo account details here, which I've already done, the next step is to define our materials. So Indalo does not use the constructions as they are set up in the VE, as we're no longer concerned about the thermal performance. We are concerned only with with materials that emit pollutants. So to assist with this process, we can use the link to create an Indalo room grouping scheme here. So I've already done that, and we can have a look at the room grouping scheme here. So I've just grouped, we can see that I have assigned rooms which share similar material properties to different material groups in my model tree here. So then using the assignment link, we can assign the desired materials to each of these material groups. So we can see that we can select up to 2 materials and 1 finish per construction element, because sometimes it's not the surface at the finish that emits the most emissions. It might be the glue behind it or some other material. We can then select different filters for supply and return from the drop-down list, with different filter groups. The return is only applicable if you have used Apache HVAC, which is our detailed HVAC modeling tool. Otherwise, you don't have return error. So if these inputs saved at the bottom here, we will then set our options for our simulation here. So we select our VE simulation result. So I'll just select the CO2 sensor strategy example, and then we can also choose the pollutants we want to consider for our results as well from this list. I'll just select all, and then we can choose our simulation time period. So because indoor air quality simulations are very computing intensive, as we'll see when we actually go on to view our results, we're only simulating a week out of our chosen month starting on a Monday. So I'll just go for the 6th of January. We then click simulate, and all of our inputs will be sent to Indalo and their cloud servers. The job reference can be used to identify our results on the Indalo platform as well, so we can just take a note of that, as can our VE project name actually as well, so that will appear on the Indalo platform. So then by clicking job status, the Indalo website will open up, and we can see our personal dashboard here with our simulation status, so whether it's preparing, waiting, finished, etc. So under the simulations tab, we can then select which results file we want to view. So this one won't run in time, so I've ran a couple of results prior, so this is one of the results we're going to look at. And so first of all, we can download an Excel file to view our results on a room by room or a pollutant by pollutant basis. So I'll just download that now. So in this case, each sheet is a room, and we have the results of all the pollutants in the columns here with a 10-minute time step provided. And the analytics feature allows us to easily visualize our data and make comparisons between our results. So we can choose to compare data from within the same simulation file, or we can compare data from different simulations, which is what we'll do today. So I'll just select my 2 simulation results files here. So on the left, we'll have our CO2 center ventilation strategy appearing in blue. 2e6, I'll just try and mute. Right, thank you. Yeah, so on the left, we'll have our CO2 sensor ventilation strategy appearing in blue, and on the right, we'll have our time clock strategy appearing in red here. So then we can select which rooms we want to analyze. So in this case, I'll just select all of our rooms, which will represent the average results of all of our rooms within each of these simulations. So the first output, we click validate, and then this will update our results for us. So the first output we come across is showing average values for our selected results variable mapped throughout the week. For example, we can see a clear accumulation of VOCs over this particular VOC over the weekend when our ventilation was set to off as per our operational profile that we set in the VE. We can also assess the outdoor values for pollutants and ratio. So if my filtration I'll just select the indoor to outdoor ratio of PM10 here, for example. So if my filtration of PM10 is efficient, the amount of PM10 should be significantly lower indoors than outdoors. So in this case, as I'm just hovering over results here, there is I don't think we've actually factored in any filtration, so we're breathing almost as much PM indoors as we are outdoors, as we can see by our sort of values there. They're quite high. So then for our scenario today, we may want to first consider indoor VOC levels for both of our strategies. So if we select an individual VOC, we'll just maybe go for a different one, such as formaldehyde. We can see that the timer clock strategy, which just to remind you is the red, is appearing in red, has lower levels than the CO2 sensor strategy, which is appearing in blue. So we can also consider outdoor air pollutants as well. We can also consider our outdoor air pollutant levels for both of our ventilation strategies. So if I select an outdoor air pollutant such as nitrogen dioxide, perhaps, we can see the time clock ventilation strategy has higher levels of outdoor pollutant in our internal spaces. So if we select another outdoor pollutant such as ozone, for example, we can see a similar pattern of results as well. If I go for PM10, as we would expect, we're seeing a similar pattern of results there with the time clock strategy having higher levels in our indoor spaces. So in this scenario, it appears by increasing ventilation through our timer clock strategy, we extract more VOCs and bring in more outdoor pollutants like nitrogen dioxide and ozone. So is it better to remove VOCs and bring in more external pollutants to breathe more particulate matter and less VOCs, or less particulate matter and more VOCs? Well, Indalo have created a useful air quality index to help us analyze such a scenario. So here I can select the air quality index, and this air quality index is the product of the concentration of pollutants multiplied by the toxicity index. So with this, we can make comparison of health issues in the building, not just concerning pollutant concentration, but taking into account the real toxicity of pollutants as well. So it can be thought of as providing an overall indication of indoor air quality. So we can also compare values of pollutants as functions of another one. So it's not just a time series. So we can select different pollutants here. So is there some proportionality or correlation between certain pollutants or parameters? This will help us to visualize this. And then lastly, at the bottom of the analytics page, we have the ability to analyze our material selection for their impact on indoor air quality. So we can view this for our entire building, as we're seeing here. So I've just selected total VOC there to display our results, or on a room by room basis if we wanted to as well. This can be used to easily understand which materials are most contributing and to test alternative materials for their impact. So if I just flick back to my slides, actually, we can look at an example of a material-based sensitivity study. So here the water-based varnish on the floor is emitting almost 2/3 of our total VOC emissions in this room. The door panel is around 8%, the acoustic ceiling 24.7%. So if we imagine that we have too much VOC compared to what our certification scheme is asking, and we have to find a solution, we can carry out a further test. So I've provided 5 simulations to Indalo, as you can see in the table there. One with a water-based varnish, one with a solvent-based varnish, and 3 standards. So standards are virtual materials emitting what the emission regulation allows at maximum. So A plus, A, B, C, this is a French regulation for VOC emission, but we can do it for other standards as well. So for glues, wooden based materials, etc. So for any kind of region, Indalo have created virtual emission materials for sensitivity studies. And we can see the results and choose the best material for our project, including also LCA, so life cycle assessment as well, and thermal simulation results, which we can of course assess using the VE, the virtual environment. And then just lastly, when it comes to selecting materials, there are 3 categories of materials in Indalo's database that we have to choose from. There are virtual materials that I was just mentioning that are not real materials, and they've been created as a threshold value for each regulation. We can also choose generic materials. So these are real materials with real properties and a description, etc., but we don't know who the producer is. Then you also have the partners materials. So you get the brand and the name of the project, and you have to pick closest to your materials. So if you can't find a specific partner material, Octopus, a specific material on the database, Octopus Labs are willing to contact the producer and create the material in the database for you. You just need to get in contact with Octopus Labs to let them know. And then this is just my last slide. Finally, there are some software requirements if you are interested in trying these tools out for yourself. The first is the VE version, so the earliest version of the VE you can use to access the Indalo Navigator is VE 2023 Feature Pack 4. The Indalo Navigator is also only included in the VE Expert Pack as well. So an Indalo license is of course also necessary to have access to the Indalo Cloud Server, which is an add-on to the VE Suite. And if you want any further information or you do have any questions about anything that I've presented today, if I could please ask you to send an email to sales@iesve.com, which you can see on the slide there. And there's also a free trial available for both of these products. So that's the VE, you've got a 30-day free trial we offer, and then the Indalo, it'd be a 15-day free trial if you're wanting to get your hands on the software. Your hands on the software yourself and give it a shot. So yeah, that really brings me to the end of my presentation. So I guess I'll hand you back over to Amr.
Thank you very much, Max. I appreciate the presentation, very thorough. So I've shared the email on the chat. If anyone wants to make a note of it, if you have any queries. I think in the interest of time, we'll conclude the session here. So thank you very much. It was very insightful, very interesting. So thank you, Max, for the presentation, and thank you all for joining. And if you have any queries regarding this innovation, please just email the sales team at IES. I've shared their email on the chat. We finished early, so get to go home earlier if you haven't got home yet. So have a brilliant evening, and thank you very much for joining once more. Thank you.
Cheers. Thanks, guys.